And another way to represent a point in 3 space is to describe it using spherical coordinates. Spherical coordinates are a little bit not set in stone. What I mean by that is if you cross-reference other textbooks or people's lectures, you might find that the ordered triples aren't always listed the same way. Almost always we use rho, which is in place kind of as r, but it's not the same thing as r from cylindrical. We use theta, which is the exact same thing as it was in cylindrical. And then we use another angle, phi. And what is really common is to see theta and phi switch positions, or even to see theta and phi describe the opposite angles. So that can be really frustrating. The best thing that I can recommend to keep those sorted out, if you are someone who likes to cross-reference other materials, is to identify the type of angle based on its name. In our book, theta is the polar angle, because it's just like the angle that we used in polar coordinates. So this is the angle that is stuck in the xy plane. Phi, this is called an azimuthal angle. I don't know if I'm spelling that right. Here we go, azimuth angle. This is how you're going to be able to tell the two apart. Again, one is the polar angle, one is the azimuth angle. Sometimes they're ordered different, where you will see the azimuth angle in the center and the polar angle, the last angle. Sometimes you'll see theta as the azimuth, and sometimes you'll see phi as the polar. So that's frustrating. Be careful when you cross-reference things. For our book, we will use theta as the polar angle to keep things consistent. Phi is the azimuth. All right, we know what the polar angle is. That's the angle that exists in the polar plane, in the r theta plane. Phi is new to us, though. Phi is an angle that starts at the positive z-axis and then drops down. This is what we're calling the azimuth angle. So in spherical coordinates, we use these 3 values. Rho, which is not like r. Remember, r in polar coordinates was flat in the polar plane. Well, in spherical, rho starts at the origin and it's the diagonal distance out to our point in space. So rho is not stuck flat in the polar plane. Rho is able to be in 3 dimensions. Theta is the polar angle that rotates from the positive x-axis or the polar axis. And then phi is our azimuth angle. Now, being able to translate between rectangular and spherical is very useful. So we're going to start first with points that are in spherical form, and we're going to convert them to rectangular using the following formulas. X is really similar to what it was when we went from cylindrical to rectangular. And if you need a reminder, it looked like r times cosine theta. But you can see that r has been replaced. What used to be r is now rho sine phi. And that's because we can draw a right triangle to help us figure out how to calculate r, even though we're not given r in spherical coordinates. So remember that this line down here in the polar plane, that is r. And as far as what we're given, we know rho, and we know phi, but we do not know r. So what we can do is copy that r value, shift it up so that it connects to our point and what would be the z-axis. So I just made a photocopy of r, and that generates a right triangle where phi is the angle that touches the origin. So to find r, we can use a trig formula to help us out, where rho is the hypotenuse. Let me draw a prettier triangle here. Rho, the hypotenuse, phi, which is our angle, we have our 90 degrees here, and we're looking for r. So what we're using is a hypotenuse and an opposite side. So if we think about our trig functions, it's sine that's going to help us find that. Sine phi is equal to opposite over hypotenuse. So we can solve this for r by multiplying rho on both sides, so that we get r is the same thing as rho sine phi. So the same equations that we had from polar will work to help us find x and y. We just have to replace r with rho sine phi. And hopefully that'll help you remember these equations, because if you memorize the polar ones, you just have to add one more bit, that r is equal to rho sine phi. And then there's one other thing that's different. Z is no longer just equal to z. We would have to find out what the z value is, and we actually use that same triangle, but this time we would be looking for the z value, so we would use cosine instead of sine. All right, now that we have those equations down, let's put them to work. So we are given rho is equal to 8, theta is equal, whoops, I wrote 5. Theta is equal to pi over 3, and phi is equal to pi over 6. So x would look like 8 sine pi over 6 cosine pi over 3. It is very important to get those angles correct. The azimuth angle goes inside of the sine. The polar angle goes inside of the cosine for x. And we could calculator that to get 2. And then for y, we'll have 8 sine pi over 6 sine pi over 3. Calculated this, we'll get 2 root 3. And then lastly, for z, we will have 8, which is rho, cosine phi, which is cosine pi over 6. And we can calculate that to get 4 root 3. So the same point, but in rectangular, would look like 2 root 3, 4 root 3. All right, let's try one more. So we have a point in spherical. Rho is -2, theta is -5 pi over 6, and phi is pi over 6. So to make this, we're going to use those same conversions. X would be -2 sine pi over 6 times cosine -5 pi over 6. And I get positive root 3 over 2. For y, that would be -2 sine pi over 6 cosine. Just kidding. For y, it's sine again. -5 pi over 6. We can calculate that. And we get 1/2. And then lastly, for z, we have rho times cosine of the azimuth angle, which is -2 pi over 6, is root 3 over 2. So this same point, but in rectangular coordinates, would look like root 3 over 2, 1/2, -root 3. For these problems, it really is just about being familiar with using equations to translate from like one language to another. It's a lot of trig memorization, so have your calculators handy or work on your trig facts. That'll make this go smoother. Just like in cylindrical coordinates, spherical coordinates map points out on the surface of spheres. So for a spherical coordinate, I like to think of the way that it's built as you start with your rho along the positive x-axis, you rotate your theta, the polar angle, and then from here, that already has created a sphere, but you need your azimuth angle to drop down an angle of phi to tell you where your point is in space. And just like in cylindrical coordinates, holding each of our values at a constant generates a different type of surface. For example, rho equals to 3, that's a sphere. Anywhere on this sphere, you could plot a point, and rho would have to be 3 if you're on the sphere. Theta and phi can be whatever you want. Theta equals pi over 3 is still a plane, just like it was in cylindrical, and then phi equals pi over 3. That allows you to have whatever theta you want. So you could rotate around the z-axis. And it allows you to have whatever rho you want. So you could go as far out and as far into the origin as you want. And this is actually starting to trace out a cone. My sketch looks terrible, but it's a cone. So in spherical, rho equals constant is a sphere, where rho is the radius of the sphere. Theta equals constant, that's still a plane. And then phi equals constant, that's a cone. Now think about the quadric surfaces that we learned in the last section. The equation for a cone in rectangular coordinates was much more difficult. And even the equation for a sphere in rectangular coordinates is much more difficult. But in spherical coordinates, spheres are described so simply, as well as cones. So hopefully this gives you a glimpse into how things can become easier once we've learned these other coordinate systems.